This video provides a high-level overview of IEC 64099, what it is and what it is not. We won't get too technical, but we'll assume you have a basic knowledge of automation and IT software concepts. If you are a technician or a manager in the automation or IT industries, and you want a general understanding of IEC 64099, this video is for you. By the end of this session, you'll understand the basic principles behind IEC 64099, and more importantly, you will have a good feel for the sorts of use cases where IEC 64099 excels. Armed with that knowledge, you'll be able to carry on your IEC 64099 journey. Let me also say that the people in this video are IEC 64099 champions. We believe that IEC 64099 is the missing link for the digitalization of industry, and that it has the potential to bridge both the IT and the OT worlds. It is a technology that engineers from both worlds can understand and work with, and this is key if the OT world is going to leverage IT technologies like artificial intelligence, machine learning, and cloud edge architectures. It will also be key in attracting the younger generation of IT-savvy engineers into the fascinating world of industrial automation. By bringing the worlds of automation and IT together, IEC 64099 will make Industry 4.0 a reality. So, let's get started. We need to look at a few basic technical concepts to set the scene. Bear with us. This will put everything that follows into context. The first thing to note is that the IEC 64099 standard was written by some of the same people that wrote the IEC 61131 standard. But let me make it clear right away that IEC 64099 is not a programming language for PLCs. In this respect, it's totally different from, but also totally complementary to IEC 61131. IEC 64099 is, in fact, a system-level design language for distributed measurement and control systems. Technical concept number 1, event-driven function blocks. The author of the standard took the well-known IEC 61131 function block concept with its data inputs and data outputs, and they added event inputs and event outputs to it. The behavior of a basic function block is defined as an event-driven state machine, the so-called execution control chart. When a transition is fired, the active state of the execution control chart changes with only one active state at any one time. When a new state is entered, the corresponding actions are executed. An action consists of an algorithm or an output event, or both. An algorithm within a basic function block can be written in any programming language. The IEC 64099 standard doesn't actually specify the programming language, but it does recommend the IEC 61131-3 languages. An algorithm can only use input data, output data, and internal data of the function block type. Therefore, a basic function block defines very strong encapsulation of algorithms, which is a key characteristic of software components. Applications are built by linking function blocks together into function block networks. And I can nest function block networks within function blocks with, in theory, no limit. Using the event inputs and outputs, I can control the execution order of the function block. By linking event outputs and data outputs to event inputs and data inputs, I effectively have very precise control of the execution order and data flow of an application. Right, now, you might be thinking, hey, so what? What's the big deal? So let me assure you that this apparently simple construct of event-driven function blocks is actually a very powerful thing indeed. Why? Well, several reasons. As we just saw, as an automation programmer, I now have strong control of when function blocks execute. But as an IT software engineer, I see something completely different. I see an object. I see a method that I can call, pass parameters to, and get back a result. Suddenly, this strange OT world of graphical function blocks starts looking familiar to me. And that's not all. Think black box. think software component. IEC 640/99 doesn't actually define the programming language, as I said before. So in theory, I can use any language, encapsulate my IP inside the black box, function box, and then someone else can take it and use it as a software component to build an application by plugging together other software components. Now we're getting somewhere. One last point. The automation world is a cyclic, periodic, scan-based world, whereas the IT world is a transactional-based world. In other words, the IT world is event-driven. So this event-driven graphical function block world is perfect for interfacing IT systems with OT systems in an efficient manner. A pure stroke of genius. One point of detail is that IEC 649 also supports periodic events if so required. We'll talk more about that later. But there's more, which brings me to technical concept number 2. Application model independent of underlying system devices. From a formal point of view, the IEC 640/99 standard is described as a list of models: an application model, a system model, and a device model. In this way, IEC 640/99 enables application-centric design by separating the application model from the system model. Application programming is done independently of the underlying control devices and communications infrastructure topology, which is defined by the system model. The system model maps and distributes one or more applications by defining which parts of the application are executed on which devices. Amongst other things, a device model manages the connection to the process interface, sensors or actuators via the device I/O bus, and to the communications interface to other devices or IT systems used by the distributed application. The combination of application, system, and device models enables applications to be designed independently of the underlying automation hardware. Once completed, the applications can be distributed across heterogeneous devices with zero programming effort, and those devices can then interoperate following standardized communication data models across networks, again, all without the need for programming. The devices I distribute the application to could be instruments or actuators, like variable speed drives. They could be small or large PLCs, or edge computing devices, like this device here. I can even distribute applications to small devices, like Raspberry Pis. Pretty cool, huh? But let's pause a second here and consider what we've discussed so far. Event-driven software components, independent of the underlying hardware devices, that can be distributed across different hardware devices, ranging from instruments and actuators to controllers to full-blown multi-core edge computers. I hope you're starting to get the picture. This is not business as usual for the automation world. In fact, I have just described a future world where instead of programming controllers, I solve complex Industry 4.0 use cases with a plug-and-produce approach, where I plug together proven in use components that I download from a rich ecosystem of smart developers to create a final application. Not only do I drastically reduce the cost of creating an application and increase its quality, but I can also now tackle complex Industry 4.0 use cases that were impossible or too expensive to tackle using classical PLC programming techniques. Anyway, enough theory. Let's talk to some people that are actually doing this today. Let me first hand over to Franco Cavadini, who will talk about how he has solved some of those cool Industry 4.0 use cases like digital twins and virtual commissioning using the IEC 640/99 standard. Franco, over to you.
Hi John, and thank you for your introduction. I honestly hope that my experience as a practitioner of IEC 640/99 will be of interest for our audience. Now, today I'd like to focus on one aspect that you actually mentioned during your speech, which is the need for operation technology and information technology to integrate seamlessly in the future of automation. You know very well that I started working with 61499 a few years ago, especially applying it within the most advanced international R&D projects. One of its technical features that immediately won me over is the way the standard merges the requirements of real-time control with the event-based nature of IT applications. In fact, well before Industry 4.0 initiative was launched, we were already implementing so-called new layers of intelligence to extend the functionalities of automation systems beyond their physical boundaries. Now, my idea is that the PLC must evolve to become the point of convergence between physical and digital. And I think that IEC 61499 is in the perfect position to be the key technological enabler of such a transition. But since you actually invited me to talk about use cases and not just about theory, let me try to provide you a few interesting examples of what we have been doing recently. Now, I'd like to start with one of the results that I am honestly most proud of, the distributed automation demonstrator that we have realized at the Como Next Innovation Hub. It is located here in Italy, in the northern part of it actually, near the Lake of Como, and it was done thanks to the Horizon 2020 program of the European Commission, under the so-called Daedalus project. Our idea at the beginning was to build a system capable of showcasing all the strengths and the potential of IEC 61499, but in an industrial-grade scenario. Through the support of several international companies, we have integrated heterogeneous systems from multiple suppliers and made them working in orchestration, thanks to 61499. One aspect in particular I'd like to focus on is the way that we have exploited event-based and the object-oriented nature of the standard to implement the so-called virtual commissioning. In fact, we have extended the design lifecycle of automation to include also digital twins of physical assets. This enables the concurrent engineer of control and simulation, empowering developers with new and powerful tools to debug faster and better their code. This innovative approach has been validated through our demonstrator, and you can actually come and see it at any time at the Como Next Innovation Hub. The second example I'd like to talk about today is from a completely different sector, but I think that it will be equally interesting. I'm talking here about the process industry. In fact, as part of a project called the Metro, we are realizing a pilot plant for chemical recycling of plastics, also called depolymerization. And the platform we use to develop its automation is obviously based on IEC 61499. Now, from a control point of view, we chose 61499 because of the high modularity of the core reactor of the process. But there is another aspect which is and was fundamental to us, the runtime adaptation of the plant working parameters. Let me explain a bit better the context. When you deal with recycling as we do, it means that your feedstock is actually a post-consumer waste, hence with the intrinsic variability that is difficult to adapt with traditional control techniques. What we want to do is to continuously optimize the process by adapting its configuration to the variability which is intrinsic to the feedstock and of other boundary conditions. For instance, the life cost of electricity. Thanks to IEC 61499, it was easy for us to develop real-time control software, but also to connect to external data analysis and optimization tools, actually leveraging on the event-based formalism and interfacing mechanism of the standard to implement it. With the Demeto pilot plant, if you want, we are actually putting together a revolutionary chemical process with a game-changing automation technology. And I'm quite sure that something good will come out from it. John, I fear the time you gave me has almost finished, so I will have to stop here, even if you know I'd gone for hours talking about these topics. I hope that my very short presentation was interesting and that it will help people understand better the potentialities IEC 61499 offers in practice. Thank you again for this opportunity and see you soon.
Let me hand over now to Gernot Kolliger to talk a little about application programming in an event-driven environment. It's quite different to the cyclic world we know today. And Gernot, as one of the world's leading specialists on IEC 61499 applications, will give you a few tips on why it's the way to go to enable Industry 4.0.
Thanks, John. Let me explain in some small examples why I'm so happy to create automation solutions with IEC 61499 and the event-driven capabilities of the standard. When I interact with the real world, I'm doing this event-based. So for example, if I want to start a pump, I turn the switch to on. As a reaction to that, a relay closes and the pump starts up. Nothing is needed to be done from the control side to keep the pump running, which also means there is no need to execute logic because nothing changes. As soon as I come back and turn the switch to off, the relay opens and the pump stops. As you can see, there were only two situations where logic must be executed. Only when the state of the switch changes, this event gets recognized and influences the pump. This works perfect for logical operations and cause-effect situations because it can directly translate the real world's behavior into an event-driven program. However, in automation, we have also the need for periodical and cyclic program execution, especially if any kind of regularity control is needed. It is easy to achieve this in an IEC 61499 program because I can just use a function block which creates a periodical event in my program logic. This generated events then triggers only that part of my logic which is needed to be calculated in a periodical manner. All the other parts are still only executed in case there is a change of an input value. Based on this paradigm, there is a huge reduction in calculation time needed for a program to run because less code gets executed which will produce the same result over and over since no input data changes at all. Another great benefit of the event-driven execution is that it works in the same manner and in the same way as most of the IT, cloud and web applications do. These kind of programs interact with method calls and notifications. The IEC 61499 standard directly supports this way of interaction because the modeling language perfectly describes the association between data and events and make it easy to use and understand them thanks to its graphical representation we have in the standard itself. A method call from the IT level program to an IEC 61499 application can be directly translated as an occurrence of an event and is received with data associated through the so-called with construct. Such method calls or notification with its associated data are unique messages exchanged between the programs. This provides guaranteed data consistency throughout the lifetime of the event execution. Nicely, all of this works inside a single controller in the same way as in a distributed automation environment with multiple controllers involved to solve an automation task. All these great capabilities allow me to solve complex automation tasks with easiness and less effort is needed for me to make it run in a distributed environment. As in great bonus, I get direct integration paths to web, cloud and IT applications to solve my customer needs in a very professional way. All of this should give you now an idea why I'm so excited about IEC 61499 and the solutions we provide in Schneider Electric. Back to you.
Thank you, Gernot. So I hope this short introduction to IEC 649 has whet your appetite and made you want to learn a lot more. And believe me, there's a lot more to learn. Check out all the links below to various offline online resources where you can learn more about IEC 61499 and refine your skill sets on this exciting emerging technology. I hope you enjoyed this video, and more importantly, I hope you enjoy your IEC 61499 journey. Thank you.